Hey everyone, and welcome back for another deep dive. This time, we're going to be talking about something that's pretty mind-bending, and that's the idea that everything around us, me, you, this, might actually be just vibrations in like a giant web of energy fields.
Whoa.
So you sent us this YouTube video called What is Almost Everything Made Of? From the History of the Universe channel.
Yeah.
And it really dives into this concept, so...
It does. It really challenges kind of what we think we know, like our everyday intuition about the world.
Yeah.
But it's based on really solid science.
Yeah.
We're really trying to get down to the fundamental building blocks of reality here.
Right. And the video starts off with this really cool analogy figuring out the universe to watching a chess game.
Oh, yeah.
But we can only see the pieces moving. Like, you can't see the actual rules of the game.
Yeah, and that's a brilliant analogy that was popularized by the physicist Richard Feynman.
Yeah.
And he really kind of hit on something there, because that is how we kind of decipher the universe, right? We observe patterns.
Right.
And we try to make rules based on those patterns, just like if you were watching a chess game, right?
Yeah.
Imagine you're watching the bishop move.
Okay.
And you're like, okay. The bishop always stays on the same color squares.
Right. Yeah.
You think, oh, that must be the rule. Then as you watch more, you realize, oh, there's a deeper principle here.
Yeah.
The bishop can only move diagonally, and that explains the color pattern.
Exactly. Yeah.
And then you start to wonder, like, well, what other kind of hidden rules are shaping this universe?
Right, yeah. And that's what's so exciting about this whole deep dive, is that we're going to try to uncover some of those hidden rules.
Exactly.
And the video really focuses on the idea of field.
Yeah.
And I think when people hear fields, they might be thinking, oh, like fields of wheat or something.
Right.
But it's a lot more than that.
It is. But actually, the idea of a field is something that we encounter all the time.
Okay.
Let's think about like a weather map. You see those lines and colors representing, temperature variations across a region.
Uh-huh.
Well, that's a temperature field.
Okay.
Every point in that space has a specific temperature associated with it.
Gotcha. Okay.
So that's a field.
All right. I can picture that. But how do we go from like temperature fields to something like, magnets attracting each other?
Well, just like temperature, you can represent other physical quantities with fields too.
Okay.
Think about the Earth's magnetic field.
Mm-hmm.
It's this invisible force, right, that extends way out into space.
Yeah.
It's what makes compasses work. And it even affects satellites.
Yeah. Speaking of satellites, the video mentions this incident with the Japanese Hitomi satellite.
Right.
What happened there?
Well, the Hitomi satellite was actually designed to study black holes and other really powerful cosmic events.
Cool.
But it ran into a bit of trouble with something called the South Atlantic anomaly.
Oh. Well.
This is a region where the Earth's magnetic field is unusually weak. And that means more radiation from space can kind of seep through.
Oh. So it kind of fried the satellite circuits?
Yeah, basically.
Ouch.
It just goes to show you that even seemingly empty space, right, can be filled with these invisible forces like magnetic fields, and they can have very real consequences.
Yeah, okay, so fields are these like invisible forces all around us.
Right.
But how do they actually explain like how magnets can, attract or repel each other without even touching? It seems like magic.
Right, it does seem like magic, but to understand that, we need to introduce the idea of field lines.
Okay.
This was something that Michael Faraday, a brilliant scientist, kind of pioneered.
Yeah.
He imagined these invisible lines extending out from the poles of a magnet.
Okay.
Right? And the closer those lines are, the stronger the magnetic force is at that point.
So when two magnets get close to each other, their field lines are interacting, and that's creating that push or pull that we feel.
Yeah, that's it. And understanding this really paved the way for a huge discovery, which was the unification of electricity and magnetism.
Oh, yeah. Now we're talking, this was James Clerk Maxwell in the 19th century, right?
Yes, James Clerk Maxwell.
Who kind of took it to the next level?
He took the equations that described electricity and magnetism and realized they weren't separate.
Oh.
They were two sides of the same coin.
Wow.
He showed that they were both manifestations of a single force, electromagnetic force.
Okay.
And his equations predicted the existence of something really interesting, electromagnetic waves.
Yeah, and what's even more wild is that the speed that he calculated for these waves matched the speed of light.
Exactly. And that was a huge deal.
Yeah. It meant that light, the stuff that we see with our eyes, is actually a form of electromagnetic radiation.
Yes. And it travels through space as a wave.
Right.
Just like ripples spreading out on a pond.
Right. But then The video throws a curveball at us with this thing called the photoelectric effect. And this showed that light can actually behave as a particle, too.
Yes.
A photon. So how can something be a wave and a particle?
It's a great question.
Yeah.
It challenged everything we thought we knew about light.
Right.
It suggested that depending on how we observe it, light can act like either one.
Wow.
And this is really one of the first hints of this strange and counterintuitive world of quantum mechanics.
Yeah, and this is where things get really interesting because this quantum weirdness led to, scientists completely rethinking the structure of the atom.
Absolutely, yeah.
Yeah.
And the video uses a very interesting example, takes us to these neon-lit streets of Dunebori, Japan.
Yeah, okay.
Which is amazing because something as simple as a neon sign could actually reveal secrets about the quantum atom.
All right, I'm all ears. What's the connection between neon lights and atoms?
Well, those bright red lights, you see them everywhere. They're actually produced by excited hydrogen atoms.
Okay.
And according to this model of the atom called the Bohr model, electrons can only exist at very specific energy levels, right? It's kind of like if you're ordering food at a restaurant.
Okay.
And you can only choose from certain portion sizes.
Gotcha. Okay.
You can't just order whatever you want.
Right.
You're stuck with the menu options.
Yeah. Okay. So the electron can't be in between energy levels.
Exactly. Yeah.
Okay.
Just like you can't order, half a small portion and half a medium portion.
Right. Yeah.
You got to pick one.
Yeah.
And when an electron jumps from a higher energy level to a lower one, it releases energy in the form of a photon.
Okay.
And the color of that light depends on the difference in energy between those two levels.
Right. And that's why we see those distinct colored lines in the hydrogen spectrum.
Exactly.
Each line represents a specific jump.
A specific energy jump, exactly.
Then there's this thing called the fine structure, where there are these closely spaced lines that the Bohr model couldn't explain.
Yes, exactly. And that was a clue that something was missing.
It's like the menu had some secret off-menu items.
Exactly. Yeah. It's like, wait a minute, there's more to this than we thought.
Right. Exactly.
So to understand that, we actually need to travel to a very special place, Westminster Abbey.
Westminster Abbey. What's at Westminster Abbey?
Well, there's a very special equation engraved there.
I'm guessing this is Paul Dirac's equation.
You got it.
Okay. The one that's almost as famous as EMC-Free?
Pretty much, yeah.
Okay, all right.
And Dirac's equation actually explained this fine structure really elegantly.
Right.
It introduced a new property of electrons called spin.
Spin, okay.
And now it's not like electrons are actually spinning like little tops, right?
Right, yeah. That always seemed a little too literal to me.
It did, right?
Yeah.
So spin is really an intrinsic quantum property of electrons.
Okay.
It's kind of like an internal angular momentum that they have.
Gotcha.
And it creates a second magnetic field.
Okay.
And that interacts with the electron's motion.
Okay.
And that's what causes those subtle energy level shifts.
So even seemingly simple particles like electrons have these hidden depths, and Dirac's equation managed to capture that.
It did. It was a huge step forward.
Wow.
And there's even more. His equation actually predicted the existence of something else, something called antimatter.
Antimatter, okay.
Specifically, a particle called the positron.
Okay.
Which is basically like the electron's opposite twin, but it has a positive charge.
Wow. Talk about a game changer.
I know, right?
So Dirac's equation was huge.
It was huge, but it wasn't quite the whole story.
Oh, there's more?
There were still some tiny discrepancies that it couldn't quite explain.
Okay.
And these discrepancies hinted at a deeper reality.
Uh-oh.
Where fields are not just some mathematical tool, but the very essence of existence itself.
All right. You've officially piqued my curiosity.
Good.
I think we need to take a break here, and then we'll come back and really dive in deep end.
Let's do it.
Okay, so we're back, and we're ready to dive into this deeper reality, those tiny discrepancies that hinted at something more. What's next on this journey of discovery?
Well, to really grasp this deeper reality, we need to talk about, believe it or not, a levitating frog.
A levitating frog? Did I miss something? Where did frogs come into this?
It sounds strange, I know. But the video uses this fascinating experiment, actually done by a physicist named Andre Geim, to make a really profound point.
Yeah.
Even we are essentially levitating.
Okay, you've got my attention. A levitating frog. Tell me more.
So Geim actually used powerful magnets to levitate different objects. And one of those objects was a frog.
No way.
Yeah, it might look like magic.
Yeah.
But it's actually a perfect illustration of the quantum world at work.
Okay.
We're not actually touching the chair we're sitting on or the ground we walk on.
Hey, I'm not actually touching my chair right now. What's going on?
Nope. We're actually hovering ever so slightly above it on a cloud of electrons.
Electrons.
Yeah, these electrons are constantly repelling each other because of electromagnetic force.
So I'm basically floating on a sea of invisible particles.
Pretty much.
Wow, that's both mind-blowing and a little freaky.
It is, isn't it? And this brings us back to those tiny discrepancies that we were talking about before. You know, the ones that Dirac's equation couldn't quite explain.
Right.
The Lamb shift and the anomalous magnetic moment of the electron.
Oh, okay, yeah.
These were actually crucial clues pointing to the true nature of quantum fields.
Okay, remind me again, what were those discrepancies? What were they about?
So the Lamb shift, it was this tiny but unexpected energy level split in the hydrogen atom.
Uh-huh.
It was like two energy levels that should have been identical were actually slightly different.
Oh, okay.
And the anomalous magnetic moment was this slight deviation in the electron's magnetic strength from what Dirac's equation predicted.
So these tiny little differences, they actually revealed something much bigger.
They did. They suggested that the electromagnetic field itself wasn't this smooth and continuous thing like we thought.
Oh, okay.
It had to be quantized, which means it comes in these discrete little packets or quanta.
Just like light, exactly.
So light can act like both a wave and a particle, and so can the electromagnetic field.
Precisely.
Yeah.
And this is where this amazing theory called quantum field theory, or QFT, comes in.
Right.
It reimagines reality in a way that's really hard to wrap your head around at first.
Okay.
It's not about particles existing within field.
Okay.
It's that particles are the field, or rather they're excitations of those fields, like vibrations.
Oh, okay. So instead of picturing an electron as a tiny ball orbiting the nucleus, we should think of it as a vibration in the electron field.
That's a great way to think about it.
Okay.
And these vibrations can interact with other fields, like the electromagnetic field. And that's what creates all these phenomena that we observe.
So when an electron absorbs a photon, for example,
it's really just a vibration in the electron field interacting with a vibration in the electromagnetic field.
That's exactly it. It's all interconnected.
Wow.
It's this beautiful dance of vibrating fields.
Okay.
The video uses this great analogy. Imagine a grid of interconnected springs.
Okay, springs.
Yeah, and if you pull on one spring, it creates this localized vibration.
Right.
And that spreads outward.
So the springs are like the field and the vibrations are like the particles.
Precisely.
Okay, I think I'm starting to get it.
Good.
But then it gets even wilder because these fields are apparently always buzzing with these things called virtual particles.
Yeah, virtual particles.
Okay, now we're back to the weird stuff. What are virtual particles?
So think of them as like these fleeting vibrations.
Okay.
They pop in and out of existence. And they're constantly borrowing energy from the vacuum of space.
The vacuum of space, okay.
Yeah, it's like the universe is playing this cosmic game of borrow and return, constantly exchanging energy.
So these virtual particles are like ghosts, just appearing and disappearing.
That's a great way to think about it, yeah.
Okay.
And even though they're fleeting, they actually have a measurable effect on the world around us.
Right, because the video explained how virtual particles help explain those discrepancies we talked about before.
They do?
The Lamb shift and the anomalous magnetic moment.
Exactly.
So how does that work?
Well, this constant creation and annihilation of virtual particles around an electron actually creates this sort of fuzzy cloud of energy.
Okay.
And that cloud actually interacts with the electron itself.
Uh-huh.
It shifts its energy level slightly and affects its magnetic property.
So those tiny discrepancies were actually caused by the quantum vacuum, the seemingly empty space that's actually full of virtual particles.
That's right. It turns out that empty space is a lot busier than we thought.
Wow. Who would have thought empty space was so complicated?
It's one of those things that just makes you go, huh. But you can imagine when physicists first started trying to calculate the effects of these virtual particles, they ran into some issues.
What kind of issues?
Well, the equations kept giving them these nonsensical answers, like infinity.
Infinities. Not again.
I know.
Did this mean quantum field theory was wrong?
Not necessarily.
Oh, right.
They developed this very clever mathematical technique called renormalization.
Normalization.
It was a way to deal with those infinities.
Okay, so was it just a mathematical trick to get rid of nonsensical answers?
It's more than just a trick.
Okay.
It's a way to make sense of the seemingly absurd.
Okay.
It involves carefully subtracting the infinite parts of the calculations, and what you're left with are these finite, measurable values.
Okay.
And those values actually match what we see in experiments.
So renormalization basically saved the day for quantum electrodynamics.
It did.
Okay, but what about the other forces of nature?
Right.
Did this approach work for them too?
That's a great question, and that's where our journey takes us next. We're going to delve into the world of the weak force.
The weak force, okay.
The force that's responsible for things like radioactive decay.
Okay.
Some of the most fundamental processes in the universe.
All right, I'm ready to dive deeper into this weak force.
Good, let's do it.
Radioactive decay always sounded kind of mysterious to me.
It is?
What exactly is going on there?
Well, the video actually uses this technique called carbon dating as a way to understand the weak force.
Carbon dating, I remember that from school.
Yeah, it's used to determine the age of ancient artifacts, right?
Right. But how does it connect to the weak force?
So carbon dating is based on the decay of carbon-14, which is a radioactive isotope of carbon.
Okay.
And what happens is carbon-14 decays into nitrogen-14 through a process called beta decay.
Beta decay. Okay.
And during this decay, a neutron in the carbon-14 nucleus transforms into a proton.
Oh, okay.
And it releases an electron and an antineutrino in the process.
So a neutron turns into a proton.
Yeah.
But what force is actually driving this transformation?
That's the weak force at work.
The weak force. Okay.
It's the only force that can actually change the flavor of a quark.
Hold on. Quarks have flavors, like ice cream.
It's not quite like ice cream flavors, but it's a helpful analogy.
Okay.
There are 6 types of quark, and each one has unique properties.
Right. We learned about those before.
Yeah, up, down, strange, charm, top, and bottom.
Right. Okay.
So during beta decay, what happens is the weak force actually changes a down quark into an up quark.
Okay.
And that transforms the neutron into a proton.
It's like switching out an ingredient in a recipe.
Exactly. And to mediate this transformation, the weak force has its own set of force-carrying particles.
Like how photons carry the electromagnetic force?
Precisely. These are called bosons.
Bosons, okay.
And the weak force has 3 of the W plus A, the WU, and the Z boson.
Okay, so 3 bosons for the weak force.
Yeah, and unlike photons, which are massless, these bosons are actually quite heavy.
Heavy bosons, okay.
And that gives us a clue about the nature of the weak force.
What do you mean? How does their mass relate to the force?
Well, their mass is actually a consequence of their incredibly short lifespan.
Okay.
Remember those virtual particles we talked about?
Mm-hmm.
The W and Z bosons are kind of like super short-lived virtual particles.
Yeah.
They pop in and out of existence very quickly.
So because they have such a short life, they have a lot of energy, and energy is equivalent to mass, right?
You got it.
Even see them.
Exactly.
Yeah.
So the weak force bosons, they're like heavy hitters that vanish quickly.
Okay.
And that explains why the weak force has such a short range.
Oh, so its range is limited because its force carriers, these bosons, they kind of disappear before they can travel very far.
That's it. They run out of steam quickly.
Okay, that makes sense.
But even though the weak source is weak, it plays a really important role in the universe.
Right.
It governs radioactive decay, which is essential for things like carbon dating.
Okay.
And it's also vital for the fusion reactions that power stars.
So it's kind of like this unsung hero working behind the scenes to shape the universe.
I like that, yeah. The unsung hero.
But the video mentioned that there was a bit of a snag when physicists tried to describe the weak force using quantum field.
Yes.
What was the problem there?
Well, the math predicted the existence of these 3 weak force bosons, right? The W plus, the Z.
Uh-huh.
But the theory only worked if they were massless.
Oh.
And we knew they had to have mass.
Right, to explain the short range of the force.
Exactly. So it was this puzzle that needed solving.
Like trying to fit a square peg in a round hole.
Pretty much, yeah.
The theory almost worked, but not quite.
Yeah, it was frustrating.
So how did they resolve this?
Well, a really brilliant idea emerged.
Okay.
What if the electromagnetic force and the weak force were actually once unified
Oh, okay.
into a single force in the early universe?
So we're going back to the Big Bang, where everything was supposedly one big unified force.
Exact. That's where the idea of the electroweak force comes in.
The electroweak force.
So the idea is that at these incredibly high energies of the very early universe,
Uh-huh.
the electromagnetic and weak forces were indistinguishable.
They were all blended together.
They were all one.
Okay.
But then as the universe cooled and expanded after the Big Bang,
Right.
something had to happen to split those forces apart.
Yeah. How did they separate?
That's where the Higgs field comes in.
The Higgs field. Okay.
Imagine it like this cosmic molasses that permeates all of space.
Cosmic molasses. Okay.
Yeah, and as the universe cooled, this Higgs field underwent a phase transition, kind of like when water freezes into ice.
Okay, I'm picturing this cosmic molasses freezing.
Right, and this freezing of the Higgs field is what gave mass to the W and Z bosons.
Oh.
And that effectively broke the electroweak symmetry.
Broke the symmetry.
Yeah, and separated the weak force from the electromagnetic force.
Wow.
But the photon, force carrier of the electromagnetic force, that remained massless.
So the Higgs field gives mass to some particles, but not others.
It does. It's pretty amazing.
Okay, but what exactly is the Higgs field and how does it work?
That's the big question. And it leads us even deeper into the heart of matter.
Okay.
We need to explore the world of quarks and gluons.
Quarks and gluons. All right, lead the way.
Let's go. So, to really understand how the Higgs field gives particles mass, we should talk about the strong force first.
Okay, the strong force.
It's unlike the weak force, which governs things like radioactive decay.
Right.
The strong force is what actually holds the nucleus of an atom together.
But wait, don't we already have the electromagnetic force for that?
Yeah.
Like holding the electrons in orbit around the nucleus?
Right.
Why do we need another force for the nucleus itself?
That's a great question.
It seems like overkill.
But think about it.
Okay.
The nucleus is packed with protons, and they all have a positive electric charge. And charges repel.
Yeah.
So why don't the protons just fly apart?
I never thought about that. You're right. Something must be holding them together.
Exactly. That's where the strong force comes in.
Okay, so it's super strong.
It's much stronger than the electromagnetic force at these tiny distances.
Okay.
It basically overpowers the repulsion between protons and binds the nucleus together.
Gotcha. So what exactly is the strong force?
Well, it's kind of like the other forces. It's mediated by particles, and these particles are called gluons.
Gluons, okay.
Yeah, they're like the glue that holds quarks together.
Right, quarks, the things inside protons and neutrons.
Exactly.
Yeah. Okay.
And now the video brings up this idea of color charge.
Color charge. This is where things get really colorful.
Sort of, yeah.
Okay.
So color charge is kind of like the charge associated with the strong force, just like electric charge is associated with the electromagnetic force.
Okay.
And quarks come in 3 colors, red, blue, and green.
So are quarks actually little colored balls bouncing around inside protons and neutrons?
Not really, no.
Okay.
It's just an analogy to help us visualize this abstract concept.
Right.
It's a purely quantum property.
Okay.
And it determines how quarks interact through the strong force.
Oh.
But the key idea is that particles made up of quarks, like protons and neutrons, they have to be color neutral.
Color neutral.
Yeah, they have to have 1 quark of each color.
So it's like mixing red, blue, and green paint. You get white.
Exactly. You need all 3 to make a neutral color.
Okay.
And this explains why you can't have a particle made of, say, just 2 red quarks.
Okay.
It would violate the rules of the strong force.
Right. It wouldn't be balanced.
Exactly. So protons and neutrons are like these perfectly balanced color palettes.
One of each.
One of each.
Okay. Oh, but where do gluons fit into all?
Well, gluons are the force carriers. They're constantly zipping back and forth between quarks,
Okay.
exchanging color charge and keeping them bound together.
Okay.
And they themselves actually carry color charge, a combination of color and anti-color.
They do.
Yeah, so they can actually change the color of the quarks they interact with.
So it's like a constant game of color swapping going on inside protons.
Exactly. It's pretty wild.
With gluons making sure everything stays color neutral.
They're like the referee.
Yeah, the color referee.
Exactly. And all of this intricate dance of quarks, gluons, and color charge is described by a theory called quantum chromodynamics,
Okay.
or QCD for short.
QCD.
And it's the theory of the strong force.
Okay.
And it's been incredibly successful at explaining how quarks behave and the structure of protons and neutrons.
So we've got QED for the electromagnetic force, quantum flavor dynamics for the weak force, and now QCD for the strong force.
You got it.
Are we seeing a pattern here?
Absolutely. Each of the fundamental forces has its own quantum field theory,
Okay.
describing how it works, its force carriers, how particles interact,
Right.
and these theories, when you put them all together.
Yeah.
That's what we call the standard model of particle physics.
Ah, the standard model. I've heard of that. That's like the holy grail of physics, right?
Well, not quite a theory of everything, but it's the closest we've got. It describes all the known fundamental particles and their interaction through the 3 forces we've been talking about.
Okay.
And it's been incredibly successful at predicting the outcome of experiments.
Wow.
It's really one of the great triumphs of modern physics.
But of course, there's a but.
There's always a but.
The video mentions this elephant in the room.
Right.
Gravity.
Gravity, the force that keeps us grounded.
Yeah, literally.
It's something we all experience every day.
Yeah.
But it's also the most mysterious of them.
Really? Why is...
Well, it doesn't quite fit into the standard model the way the other forces.
Oh, okay.
Our best description of gravity actually comes from Einstein's theory of general relativity.
General relativity. Oh.
And it's very different from how we describe the other force.
How so?
Instead of thinking of gravity as a force mediated by particles like the other forces,
Okay.
general relativity sees gravity as a consequence of the curvature of space-time.
Space. What's space-time?
So space-time is kind of like the fabric of the universe. And massive objects actually warp this fabric.
Okay, I'm trying to picture this. So it's like if you put a bowling ball on a trampoline.
Exactly. That's a great analogy.
Okay.
The bowling ball creates a dip in the surface.
Right.
And in the same way, massive objects like stars and planets, they create a curvature in space-time.
So the Earth is orbiting the sun because it's caught in the sun's space-time dip.
It's a simplified way to think about it, but yeah, essentially.
Wow, that's crazy.
It is, right? Objects follow the curvature of space-time, and that's what we perceive as gravity.
Okay, so general relativity works really well for big things like planets and stars.
It does, yeah.
But why can't we just merge it with the standard model and have a complete picture?
That's the problem.
Okay.
They don't play nicely together.
They don't.
No, general relativity and quantum field theory, the framework of the standard model, they're fundamentally incompatible.
Really? What happens when you try to put them together?
Well, the math just doesn't work out. You get all sorts of nonsensical answers like infinities popping up everywhere.
Oh no, not infinities again.
I know, right?
And we can't use that renormalization trick.
Unfortunately not. It doesn't seem to work for gravity.
So we're stuck with two really successful theories that just refuse to work together.
For now, yeah.
But I'm guessing physicists aren't giving up that easily?
Of course not. There are some brilliant minds working on this problem.
Okay, what are some of the ideas they're exploring?
Well, there are two main contenders.
Okay.
String theory and loop quantum gravity.
Okay, I've heard of more.
So string theory basically says that the fundamental building blocks of the universe aren't particles,
Okay.
but tiny little vibrating strings.
Strings.
Yeah, and the way these strings vibrate determines the properties of the particles we see.
So it's like each particle is a tiny little string, and the different vibrations create the different particles?
Exactly, like different notes on a musical
I
instrument.
love that. It's all about the music of the universe.
Yeah, it is, in a way.
So that's string theory. What about loop quantum gravity?
So loop quantum gravity suggests that space-time itself is quantized.
Quantized.
Yeah, it means it comes in these discrete little chunks,
Wow.
like tiny loops all woven together.
So instead of smooth, continuous space-time, it's more like a fabric made of these loops.
Exactly. And these loops interact with each other. And that's what gives rise to the force of gravity.
Wow. So no need for a graviton particle in that.
Nope. Gravity emerges from the interactions of the loops themselves.
That's a very different way of looking at things. So which one is more like right? String theory or loop quantum gravity?
That's the big question. And honestly, we don't know yet.
Oh,
They're both still very much works in progress.
okay.
And they both have their own challenges.
Right.
Especially when it comes to making predictions that we can actually test with experiments.
So the quest for a theory of everything, a theory that unites gravity with the standard model, it's still ongoing.
It is. It's one of the biggest mysteries in physics today.
Wow. This has been an incredible deep dive. We've gone from magnets to levitating frogs to the very fabric of the universe.
It's been quite a journey.
It has, and it really makes you realize how much we still don't know.
Yeah, we've come a long way.
Right.
But the universe is full of surprises.
Absolutely. So to everyone listening out there, keep asking those questions.
Yes, keep exploring.
Keep that curiosity alive, because who knows what amazing discoveries are waiting for us out there.
Exactly. The universe is a vast and mysterious place, and there's always more to learn.
Well said. Thanks for joining us on this deep dive, everyone. Until next time.